Hello everyone, welcome back to my channel. In this video, I'll be solving the 2024 Kangaroo Math Competition problems. These problems are intended for grades 11 and 12 students. Alright, so there are 30 items in this test, all multiple choice items. Alright, let's start with item number 1. The angles in a triangle are in the ratio 1:3:5. What is the biggest of those angles? Alright, so this is a simplified ratio, so we can represent the original numbers or measures by x, 3x, and 5x. Since the sum of the interior angles of a triangle is 180 degrees, then x plus 3x plus 5x must be equal to 180 degrees. Summing up the terms in the left hand side, we have 9x equals 180 degrees. And then dividing both sides by 9, x must be equal to 20 degrees. Alright, now we want the biggest angle, so we sub in x equals 20 in the expression 5x, or in the term 5x. So we have 5x equals 5 times 20 degrees equals 100 degrees. Okay, so the answer is option C. Let's have item number 2. A tile pattern is made up of a number of identical irregular pentagons. Which of the following tiles fits into the hole in such a way that a closed curve is formed? Alright, so because we want a closed curve, we must connect this one here and the other one here. Alright, now if you look at the options, the figure is actually rotated from the original one. The base is at the top, while in the options the bases are at the bottom. So if you try to rotate this figure here by 180 degrees, you will exactly come up with the figure in option C. Alright, so the answer is letter C. Next item. Which of the following numbers is 2 less than a multiple of 10, 2 more than a square number, and 2 times a prime number? Alright, so let's start with the first condition. It says here that the number is 2 less than a multiple of 10. Obviously, 6 is not 2 less than a multiple of 10, so we can eliminate that one. All the rest are 2 less than a multiple of 10. Now the next condition says the number is 2 more than a square. Obviously, 18 is 2 more than a square, 2 more than 16. 38 is 2 more than 36, which is a square. 58 is not 2 more than a square. Okay, so we eliminate that one as well. The same is true for option A. 78 is not 2 more than a square, so we will eliminate that. Third condition, the number is also 2 times a prime number. Take note that 18 is 2 times 9, and 9 is not a prime number. On the other hand, 38 is 2 times 19, and 19 is a prime number. So the answer here is option C. Let's have item number 4. A kangaroo cuts a pizza into 6 pieces of equal size. After it has eaten one piece, it rearranges the remaining pieces so that the gaps between the pieces are all equally big. What is the angle in each gap? Alright, originally there are 6 pieces. Let us compute first the angle formed by each piece. This angle right here. Since the total measure is 360 degrees, we can divide 360 degrees by 6 since there are 6 pieces or slices. So each slice will form 60 degrees, right? So this one is 60 degrees. Now after removing one slice from the pizza and rearranging the remaining slices, we have these gaps. Alright. The sum of the measures of these gaps, or the degree measures of these gaps, must be equal to 60 degrees as well, right? Because it's the space originally occupied by the piece which was taken. So how many gaps are there? 1, 2, 3, 4, 5. So let's divide 60 degrees by 5. So 60 degrees divided by 5, that's equal to 12 degrees, right? So the answer here is option E. Next item, number 5. Julia has the strange habit of drawing the xy plane with the positive directions of the coordinate axis pointing to the left and downwards. What does the graph of the equation y equals x plus 1 look like in Julia's coordinate system? Let's draw first the correct graph of y equals x plus 1 using the correct positioning of the axis. And then we'll just apply the conditions given in the problem by flipping the x and the y axis. Okay, so using the correct Cartesian plane, the y-axis, the positive y-axis is here, the positive x-axis is here, right? And the graph of y equals x plus 1 passes through the point 0, 1 and negative 1, 0. So the graph of y equals, the correct graph of y equals x plus 1 is this. Okay, now it says in the conditions that the directions are being flipped. So instead of having the positive y-axis above the horizontal line, it's below the horizontal line. So let's flip the y-axis. Let's create another one with the flipped y-axis, positive part of the y-axis below the horizontal line. So it means that this one is being transferred in this point, right? So the new graph now intersects this point. So the new graph looks like this. Alright. Now it also says that the x-axis is also being reversed so that the positive part is in the left side. In other words, we also flip this part of the graph. Alright. So the positive part of the x-axis is now here. The graph still passes through this point, but the other point is here already. Alright, so this is what we are looking for, and that is option D. Item number 6. Kaito has manipulated a die. The probabilities of rolling a 2, 3, 4, or 5 are still 1 over 6 each for each number. But the probability of rolling a 6 is now twice the probability of rolling a 1. Alright, let's list down first the possible outcomes. There are 6 possible outcomes. So we have outcomes 1, 2, 3, 4, 5, 6. Probabilities. We don't know the probabilities for 1 and 6, but we know that 2, 3, 4, and 5 are all equally likely to come out. So it's given that each of these has probability of 1 over 6. Now, the other condition states that the probability of rolling a 6 is now twice the probability of rolling a 1. Since we don't know the probability of rolling a 1, let's represent that one by P. And so that of 6 is 2p. Alright. Now the sum of the probabilities is equal to 1. So we have the equation 3p plus 4 over 6 equals 1. Rearranging, we must get 3p equals 1 minus 2/3. So 3p equals 1/3. So p is equal to 1 over 9. But we are asked about the probability of rolling a 6. And it is twice 2p, and it is twice the value of p, right? So the answer is 2 times 1 over 9, which is equal to 2 over 9. So that's option D. Alright, let's have item number 7. Which of the following expressions has the same value as 16 raised to 15 repeated 4 times in the sum? Alright. Take note that since it is repeated 4 times, we can write the original expression as 4 times 16 raised to 15. Now, if you look at the options, the bases are all in 4, right? So we can apply the laws of exponents so that we can transform this number into an equivalent form with a base of 4, right? Now, take note that 16 is the same as 4 squared. So we can write this one as 4 times 4 squared raised to 15. Multiplying 15 and 2, we get 4 times 4 raised to 30. And finally, the 4 outside the parentheses has an exponent of 1. So we have 4 raised to 1 plus 30. That's 4 raised to 31. So this given expression is equivalent to or has the same value as 4 raised to 31, and that's option A. Item number 8. There are 6 coins on a table, each with heads facing upwards. On each move, we turn over exactly 4 of the coins. What is the minimum number of moves we must make such that all coins are left with heads facing downwards? Alright, so let's draw first the 6 coins. 1, 2, 3, 4, 5, 6. So originally, the heads are shown, right? So heads. Okay. We don't know yet how many moves we can make, the minimum number of moves we can make, so that at the end of the last move, we will have all heads facing downwards. Now we can choose any 4 coins for our first move, but I'll just choose the first 4 just to simplify the solution. So if for our first move, we can flip the first 4 coins so that we will have tails for the first 4 coins for the first move. And then the last 2 coins are still heads up. Alright. Now, we can choose the last 4 coins to flip. However, the result would be tail, tail, head, head, tail, tail. So we come up with the same result as the first move, right? However, if we choose the last 3 tails and then the following head to flip, then we would have tail and then head, 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 and this one tail. This one remains the same. And in the third move, we can choose these 3 and the last head to flip so that all of them will be tails. So tail, 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 tail. Alright, so the minimum number of moves we can make so that at the end the outcomes are all tails is 3. That's option B. You can check this one by trying the other possibilities. This is the minimum number of moves that must be made so that the outcome at the end are all tails. Number 9. Noah starts with the number 1 and multiplies it with either 6 or 10. He then multiplies the result again by either 6 or 10. He repeats this process several times. Which of the following numbers can he not obtain in this way? Since the numbers used are only 6 and 10, the product must be of the form 6 raised to a times 10 raised to b, where a and b are positive integers, or even non-negative integers, because it's possible for a or b to be 0. It's possible because Noah can choose to have only 6 as factors or 10 as factor. Okay. Now let's examine which option can be written in the form 6 raised to a times 10 raised to b. If we can find an option that does not follow this form, then that's the answer we are looking for, because we are looking for a number that is not possible to have after the process is being done. All right. Now let's manipulate option A. So we have 2 raised to 100 times 3 raised to 20 times 5 raised to 80. Take note, you want the form 6 raised to a times 10 raised to b. So what I'm going to do is to split 2 raised to 100 into 2 raised to 20 and 2 raised to 80. So and then rearrange the factors. So we have 2 raised to 20 times 3 raised to 20 times 2 raised to 80 times 5 raised to 80. This is the same as 2 times 3 by applying the laws of exponents. 2 times 3 raised to 20 times 2 times 5 raised to 80. And obviously, this is of the form 6 raised to a times 10 raised to b, because this is equal to 6 raised to 20 times 10 raised to 80. Alright? So option A is not the answer. Now let's try option B. We have 2 raised to 90 times 3 raised to 30 times 5 raised to 80. Alright. I'll split 2 raised to 90 into 2 raised to 30 and 2 raised to 60. So we have 2 raised to 30 times 3 raised to 30 times 2 raised to 60 times 5 raised to 80. And then I'll split 5 raised to 80 into 5 raised to 60 and 5 raised to 20. So I'll make this one 5 raised to 60, 5 raised to 20. So this is 5 raised to 60 times 5 raised to 20. So we have 2 times 3 raised to 30 times 2 times 5 raised to 60, right, times 5 raised to 20. Now obviously it's not of the form 6 raised to a times 10 raised to b, because this is 6 raised to 30 times 10 raised to 60, and we have an extra factor which is 5 raised to 20. Alright, so we don't have to try out C, D, and E. The answer is option B. But if you want to check C, D, and E, you can do that. Okay, so we have item number 10. There are black and dashed paths in a park. Alright, both paths divide the area of the park exactly in half. Also, so this one divides the figure into 2 equal parts. The same is true with the dashed curve. Now the question is, which of the following statements about the areas of the sections A, B, and C is definitely correct? Alright. Now, let us represent this area by D. Okay. Now, focus on the area to the left of the black curve, the solid curve. The area to the left of the solid curve is B plus D. Okay. Now, focus on the dashed paths or curve. Okay. The area to the left of that dashed path is the sum A plus C plus D, right? So A plus C plus D. Since the two paths divide the entire park into two equal parts, then we can say these two expressions represent the same area. In other words, they must be equal, right? Now, both sides have the term D, so we can cancel that out. We can transpose that, so the remaining equation is B equals A plus C. Alright, so the answer here is option B. Problem 11. John has black and white unit cubes and wants to use 27 of them to build a 3x3x3 cube. He wants to make sure that the surface is exactly half white and half black. What is the minimum number of black cubes that he needs? Alright, let's count first the total number of unit squares. Since there are 6 faces in a cube, and in this cube there are 9 unit squares in each face, the total number of unit squares is 6 times 9, which is 54. So John wants 27 of these unit squares to be black. Now the question is, how many, or what's the minimum number of black cubes to make this happen? How many, what's the smallest number of black cubes to be used to make this happen? Alright. Notice that the cubes with the most number of exposed faces are the corner cubes. So the corner cubes must be black. Alright. Because if we choose any other cube to be black, for example, this one, this cube only contributes 1 black unit squares that's visible in the surface, right? So we must choose the corner cubes instead of the center cubes in one face. Okay, so let's color the corner cubes with black just to illustrate and to track the process. Okay, so this time, how many black unit squares do we have? So each corner cube contributes 3 black unit squares. So there is now a total of 8 times 3, 24 black unit squares. We need 3 more black unit squares. Now we can choose this cube to be black so that it will contribute 2 more black unit squares. That's 1 additional cube. Okay, we now have 9 black cubes. We need 1 more black unit square. So we can just choose any of the center unit squares to be black. So we can choose this one to be black. So the cube containing this unit square is black. So we have another one. So this one contributes 2 black unit squares. This another cube contributes 1 black unit square. So that's a total of 27 already. So we have satisfied the condition. So how many black cubes do we have? What's the minimum number of black cubes to be used? We just add this. The answer is 10. So 10 is not among the options from A to D. So the answer is option E. So it must be another number. Let's have Problem 12. In a square with side length 6, a diagonal, a semicircle, and a quarter circle are drawn as shown. What is the area of the gray region? Alright. So this problem seems complicated. It appears complicated, but let's find a simpler method to use this to solve this one. What I'm going to do first is draw the other diagonal, this one, passing through the center, which is this point, and then to the other corner. What do you notice now? Notice that this area is exactly identical to this area. So they must be of the same measure, right? Similarly, this area is identical to this area. So instead of finding the area of each gray region, we can just find the area of this triangle to solve the problem, right? Now we know that the side length of the square is 6. So this is 6, this is 6. So the area of the square is 36. And this triangle is 1/4 of the entire square. So just get 1/4 of 36 divided by 4. The area of this triangle must be 9 square units. So the area of the total area of the gray regions must also be 9. Alright? So the answer is option A. Problem number 13. The diagram shows 4 squares with the entire configuration resting on a horizontal straight line. So how many squares are there? There are 4 squares. The smaller squares have side lengths A, B, and C. Alright? And then the vertices A and C of 2 small squares coincide with diagonally opposite vertices of the big square. The vertex B of the third small square lies on a side of the big square. Which of the following expressions is equal to the side length of the big square? Alright, so again, just like the previous item, this appears to be complicated, but if you see some squares and some triangles, maybe we can look at the angles also, find some similar or maybe congruent parts. Okay, so what I'm going to do first is extend this side up to the bottom. So I'll draw this segment perpendicular to the base of the square. Now, since this is a square, this one must be 90 degrees. Alright? Let's represent this angle by alpha. This one is obviously 90 because this is a square. This angle here must be 180 degrees minus 90 degrees minus alpha. So that's equal to 90 degrees minus alpha. Alright, so that angle, so I'll just label it, so that's 90 degrees minus alpha. Alright, okay, so we have determined the other angle. Now how about this angle? That is just 90 degrees. I mean 180 degrees minus 90 degrees minus 90 degrees minus alpha. Let's simplify this. This is 180 degrees minus 180 degrees. If we distribute this negative sign, we will have here minus 180 degrees and then plus alpha. So that's equal to alpha, because you can cancel that. That's alpha. So this one is alpha. Now if you look at this triangle, this one, we have an alpha here, we have an alpha here. This one's 90, this one's 90. It means that this angle right here must be 90 degrees minus alpha as well. So 90 degrees minus alpha. Now, since in a square all sides are equal, this segment must be equal to this segment. So what does this tell us? This tells us that the two triangles are actually congruent by ASA congruence theorem, right? Because this angle is equal to this angle is equal to this angle, and the hypotenuse of each right triangle is equal to one another, right? So by ASA, the two triangles are congruent. Now, what's the measure of this side? The measure of that side is A plus B. And since they are congruent, the measure of this is also A plus B. Alright? Now, how about this side? This side is C. Now, if we represent this side by x, we can use the Pythagorean theorem to have the equation x squared equals the square of a plus b plus c squared. And finally, if you get the square root, x equals the square root of a plus b squared plus c squared. Alright, so the answer is obviously option C. Let's have the next item, 14. We are given two positive numbers, x and y, with x less than y. Which of the following expressions has the biggest value? We can be rigorous about our solution by manipulating each expression, but the simplest way we can solve this problem, though less or not really rigorous, is just by substituting or choosing any values of x and y and then plugging in these values and then compare the resulting values. Suppose x is equal to 1 and y is equal to 2. Take note, x is less than y. That's why we choose a number, a value for x that's less than the value for y. If we substitute this one to the expression in option A, we must have 7 over 4 as the value. For option B, we have 5 over 3 as the value. Alright. Now for option C, we have 3 halves. For option D, we have 4 thirds. And for option C, we have 5 over 4. Alright, now we can just compare these values, and obviously the largest is 7 over 4. So the answer is option A. Again, you can also manipulate the expression, but that would take a longer time to finish. Alright, so just make you just get the LCD if you want that solution. Okay. Next, item 15. The following shape is composed of identical squares. What is the maximum number of 2 by 1 dominoes that can be placed on the shape if each covers exactly 2 squares? The dominoes can be placed horizontally or vertically and are not allowed to cover each other. Alright, so any it can be vertical or it can be horizontal. So what I'm going to do is to start at the extreme parts. For example, I can color this with I can fill in this with the shape, this one. So I'm just going to use a line to indicate the process of putting the 2 by 1 domino on the figure. Okay, so it can be horizontal or vertical line. And then I can have this one. What else? I can have this one. So what we can really do here is to minimize the areas which are not filled in. Okay, so after that we cannot put horizontal, so I can put here horizontal domino, another one. Okay, now you can check that however you place the dominoes, whether vertical or horizontal, you can just have this 10. Alright, so let's check if it's really 10. 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so the answer must be 10. You can easily check that it's not possible for uh, the answer to be 11 and 12, no matter how you um, place the dominoes, and no matter how many horizontal or vertical placements you will have. Alright, problem 16. How many 3-digit numbers are there that contain at least one of the digits 1, 2, or 3? Solving this problem directly might require a lengthy solution, since we might consider several cases following the conditions of the problem. Now let's think of another approach. What if we count first the total number of 3-digit numbers and also the number of 3-digit numbers that do not contain 1, 2, or 3, and then finally subtract these numbers to get the required count for the 3-digit numbers that contain at least one of 1, 2, or 3. Okay, so the options for the digits are 0, 1, 2, up to 9, right? 5, 6, 7, 8, 9. So there are a total of 10 options. Since it's a 3-digit number and the hundredths digit cannot be 0, we have 9 options for the hundredths digit times 10 options for the tens digit, since we can now use the digit 0, and similarly we have 10 options for the units digit for the same reason. So the total number of 3-digit numbers is 900. Alright, now let's count the number of 3-digit numbers that do not contain 1, 2, or 3. This time we have to eliminate 1, 2, and 3. Alright, now for the hundredths digit we also exclude 0, so we have 1, 2, 3, 4, 5, 6 options for the hundredths digit. But for the tens and units digit we can use 0, so we have 7 options for the tens digit and 7 options for the units digit. So this gives us about 294 3-digit numbers that do not contain the digits 1, 2, or 3. So the number of numbers, 3-digit numbers that contain at least one of the digits 1, 2, or 3 is just the difference between these two, right? So 900 minus 294, that is equal to 606. So that's option E. Problem 16. A teacher writes the 7 digits shown on the board. He asks a student to insert some multiplication signs in such a way that the product of the resulting numbers, possibly with multiple digits, has the value 20, 24. How many multiplication signs must be inserted? So let's factor first 2024. Take note that 2024, the prime factorization of 2024 is 2 raised to 3 times 11 times 23. So from this prime factorization of 2024, it's clear that we treat the first two digits 1 1 as a single number, so that's 11, and the last two digits 2 3 as a single number again, so that's 23. And because 2 raised to 3 is 8, we must insert here two multiplication signs. 2 times 2 times 2, that's 8, or 2 raised to 3. Another multiplication sign here, and the last multiplication sign here. So we have 11 times 2 times 2 times 2 times 23. Alright? 11, 23. Alright. So there are 1, 2, 3, 4 multiplication signs needed. So the answer is option D. Okay, so we have problem 18. A beaver wants to color the squares and triangles in the pattern so that adjacent cells are never the same color, even if they only touch each other in one corner. What is the minimum number of colors he needs? Okay, so if you focus on the square, and by the condition of the problem that touching parts even at the vertex must not have the same color, it is clear that the 5 regions in this square must have different colors. For example, so I'll just use a different color for the pen. So for example, I can color this one red, this one green, this one yellow, this one blue, this one orange. Okay, so it's necessary that all these 5 regions must have different colors because they meet at this vertex. Alright, this one right here. Now, how do we apply this reasoning to the other squares? Actually, this exactly applies to the other squares. Now, if you focus, so let me use another color again. If you focus on this square, take note that we already have here blue and orange, right? So I can just color this one with yellow. The next part would be green, let's say, and this one red. And this again satisfies the conditions in the problem. Alright, now you can just repeat applying this process until you color all the regions in the bigger figure, and no adjacent parts will have the same color, right? So the minimum number of colors that is needed is just 5. That's letter C. Alright, so let's have problem number 19. For problem number 19, we have we know of a positive integer n that exactly one of the following statements is true, which is the true statement. Alright, so let's just assume a certain value of n and then try to see if each statement is true or false. Alright, so our goal here is to have 4 statements false and the remaining 1 statement to be true. So what if we assume that n equals 1? So if n equals 1, then option A must be false, option B is also false, option C is true, option D is false, and option E is false. So with this assumption, the condition or the given conditions have been satisfied. So n must be equal to 1, and the only true statement is option C. So this is the answer. Problem number 20. 2 candles of equal length are lit at the same time. One candle will burn down completely in 4 hours and the other in 5 hours. Both burn at a constant rate. How many hours do they have to burn until one candle is exactly 3 times as long as the other. Okay, so let's determine first the rate of each candle. Let's say the candles are A and B. Okay, this is for A. This one is for B. So the rate at which candle A is burning is 1/4. And the rate at which candle B is burning is 1/5. Since we are looking for the time, let's represent the time by T. Now, after T hours of burning, the amount of material that is burned in candle A must be 1/4 times T. And that of candle B must be 1/5 times T. Okay? Let's say burned part. Or the part that is gone. Okay? So that's 1/4 T. The other one is 1/5 T. Since the two candles are of equal length, we can just assume that candle A has a length of 1 unit and candle B also has a length of 1 unit. So the amount that's remaining in candles A and B after T hours must be, so remaining amount must be 1 minus 1/4 T. The other one is 1 minus 1/5 T. So by this time, which candle is shorter or longer? Take note that candle A burns faster than candle B. So this must be 1/5 times T. So I'll change that. This must be 1/5 times T. Again, candle A burns faster than candle B. So after T hours, candle A must be shorter than candle B. Now, the last condition given is that after such number of hours, one candle is exactly 3 times as long as the other. Since by this time candle A is shorter than candle B, we must have 3 times 1 minus 1/4 T equals 1 minus 1/5 T. Alright? And not the other way around, because candle B is longer by that time. Now let us distribute. So this is 3 minus 3/4 T equals 1 minus 1/5 T. Okay. Let us combine like terms. I'm going to transpose 3 to the right and 1/5 T to the left. So we have 1/5 T minus 3/4 T is equal to 1 minus 3. Alright, now LCD is 20. So the numerator in the left side is 4 times T minus 15T, which is equal to -2. Okay. So the numerator in the left side is -11T. That's divided by 20 equals -2. By cross multiplication, we get positive 40 over 11. So after 40 over 11 hours, one candle is the length of one candle is 3 times the length of the other. So the answer is option A. Next, we have problem 21. A three-sided pyramid has edges with side lengths 5, 6, 7, 8, 9, and 10. The points M, N, P, Q, R, and S are the midpoints of the edges as shown in the diagram. What is the total length of the closed polyline MNPQRSM? Alright. Recall that we have the so-called midline or mid-segment theorem. So what does this tell us? The midline or mid-segment theorem tells us that in a triangle, the segment that connects the midpoints of two sides, suppose this one and this one, let's say MN. So that segment is parallel to the base of the triangle and is half the measure of the base. So if let's say the triangle is ABC, that means that MN is equal to 1/2 BC. Okay, so now we will apply this theorem to the problem. So we are looking for MN plus NP plus PQ plus QR plus RS plus SM. Okay, now what is MN? You focus on this triangle. All right, focus on the triangle and take note that MN is parallel to BC. So MN is half of 10, so that's 5, right? That's 5. NP, this one, is parallel to AD. AD is 5, right? So let's get half of AD, so that's 2.5. So this one is 2.5. PQ. PQ is parallel to AC, which is 6. So half of 6 is 3. So that's 3. QR. QR is parallel to AB. AB is 7. So QR is 3.5. RS, on the other hand, is parallel to CD. And CD is 8. So half of 8, that's 4. And finally, we have SM. SM is parallel to AC. And take note, AC is 6. Half of 6 is 3. Now we just need to add all of these numbers. Okay, so let's add the whole numbers first. So 5, 3, that's 8. Plus 4, that's 12. Plus 3, 15. Plus 2.5 plus 3.5, that is 21. Alright, so the answer is option C. Problem 22. A quadrilateral ABCD has two right angles in the vertices B and C. It is known that AB equals 4, BC equals 8, and CD equals 2. What is the smallest possible value of AX plus DX if X is a point on the segment BC? We can solve this problem by applying calculus, but I'm going to show you a solution that involves construction. To get started, let us extend segment AB beyond B to point E, such that AB is congruent to BE. Let's connect points E and C. Let us also connect points E and X. Alright, now this one is a right angle, and since BE is just an extension of AB, this one is also a right angle. Now notice that by construction again, AB is congruent to EB. So I'm just going to write that BX is congruent to itself by reflexivity, and angle ABX is congruent to angle EBX. Okay? And so by SAS congruence theorem, triangle ABX must be congruent to triangle EBX. Right? If the two triangles are congruent, then their corresponding parts are congruent as well. So AX must be congruent to EX, right? And originally we are going to find AX plus DX, the minimum possible value of AX plus DX, right? So AX plus DX, since AX is equal to EX, must be equal to EX plus DX. Okay? So if you can find the value of EX plus DX, then that's also the value of AX plus DX. So why did we construct all these additional parts? Take note that it's easier to find the minimum value of EX plus DX. Why? Because if you can recall, point X is only an arbitrary point on BX. So we can choose X to lie on the segment connecting points E and D, right? Because it gives us the minimum distance between E and D, right? So if we connect E and D, we get this segment, and we can just say that this is point X. Okay? So any other location of point X will not give us the minimum value of EX plus DX. It's only this point right here. Okay? Now, let's use the given values for the other segments to find ED. Okay? That's EX plus DX. Take note that AB is 4, and since AB is equal to EB, EB must also be 4. And we also know that BC is 8. So I'm going to mark that one. So this is 8. And CD is 2. Now, how can we find ED? Let's find some right triangles, or let's create a right triangle by extending DC. Okay. And then also extend E to the right, so that the segments we are drawing are perpendicular to one another. Okay? So we are now forming a right triangle. So what is that right triangle? If we say this is point F, then point EDF is a right triangle. Now take note that we are constructing CF such that BE is also equal to CF, and so CF must be 4. Alright? Now, BC, take note, is 8, so EF is also 8. So, ED, which is equal to EX plus DX, take note, that's equal to ED. And by the Pythagorean theorem, ED is equal to 8 squared plus 6 squared. This one is 6, right? So 6 squared, that's equal to the square root of 64 plus 36, or square root of 100, which is equal to 10. So this is the minimum value of AX plus DX. And that is option D. Let's have problem 23. We have 6 cards, and there is one number written on each side of each card. The pairs of numbers on the cards are 5, 12, 3, 11, 0, 16, 7, 8, 4, 14, and 9, 10. The cards can be placed in the empty squares in any order with any side up. What is the smallest possible result of the calculation? Alright, so we can attempt to guess and check by placing the smaller numbers in the first three boxes and the larger ones in the last three boxes, because in that way we can get a very small negative number, right? So that's how we are going to solve this one. You can easily check that by placing 3, 7, 0 in the first three boxes, 3, 7, 0, and by placing 12, what else, 14 and 10 in the last three boxes, you will get the smallest possible result of the calculation. So 10, so this one is 10, this one is 26, so not 26, 36, right? So 10 minus 36, that gives us negative 26. Okay, so the answer is option D. Let's have problem 24. I have a 4-digit number n which is equal to PQRS. If I place a decimal point between the digits Q and R, I obtain the number PQ point RS. This is exactly the average of the two numbers PQ and RS. Alright, so what is the sum of the digits of n? So if we take the average of PQ and RS, so PQ plus RS, divide this by 2, the result is PQ point RS. Okay, so how can we write the right hand side in a form that will allow us to simplify the equation? Take note that we can remove the decimal point by writing PQ point RS into PQ plus RS over 100, right? So the left hand side is still the same. Now the next steps will be simplifying the equation. We can multiply both sides by 100 to eliminate the denominator. So we have 50 PQ plus 50 RS equals 100 PQ plus RS. Now let's combine like terms. Let's move this one to the left, this one to the right. So we will have 50 PQ minus 100 PQ, that's negative 50 PQ, equals negative 49 RS. Now if we divide both sides by negative 50 RS, we'll cancel negative 50. The right hand side will be positive. So we have PQ over RS equals positive 49 over 50. So this must be the original numbers, because if this is the simplified fraction, then the original number would be a number with more than 4 digits. So this must be the original numbers, 4950. So PQ RS, P is 4, Q is 9, R is 5, and S is 0. So we are finding the sum of the digits. And by the way, the number we are looking for is 4950. So the sum of the digits P plus Q plus R plus S is equal to 4 plus 9 plus 5 plus 0. That's equal to 13 plus 5. That's equal to 18. So that's option B. Let's have problem number 25. The diagram shows an object composed of 7 cubes with edge length 2. How long is the shortest path from M to N on the surface of the object? Alright, so you can try tracing some paths on the figure, but the way to solve this is to uh, think of a way of transforming the object into another form so that we can easily find that minimum path that we want. All right, so what I'm going to do now is I'm going to mark some of the faces on the original figure just to illustrate easily what I'm going to do. So I'm going to mark this face, let's say a 1, this one 2, this one 3, 4, this one 5, 6. All right, so what I'm going to do is just to remove faces 1, 2, 3, 4, 5, and 6 from the original figure, and then flatten out these faces so that they will be leveled with the two faces on top. Okay, so I'll draw the two faces on top first. Okay, and we take note that each edge of the faces measures 2 units. Now, faces 1 and 2 leveled with the initial faces on top. Take note, this is 1 and 2. And then 3. So this is 3. This one 4. This one 5, 6, 5, 6. Alright, so this is actually point M here. This one is N, point N. Now, if we connect the 2 points, we actually get the shortest distance between points M and N. So how are we going to compute that? Take note that we can actually create a right triangle. So we can just extend this, right, and this one, and it's possible to determine the size of the right triangle because we know that this is 2, this is 2, 2, 2. So this one is 4, right? And so the whole thing, this one, must be 8. Similarly, since this is 2, this is also 2. And this one, the whole thing is 6. And so by the Pythagorean theorem, we can just solve Mn. So we have Mn, I wrote D, so it must be Mn. So Mn is equal to the square root of 8 squared plus 6 squared, which is equal to 64 plus 36. That's equal to the square root of 100, which is equal to 10. Alright. Now, if we trace this path on the original figure, it looks like this. Alright. Okay, so here, and then, so this is 2. Okay, so here, here, and here. So it does not look like a straight line if traced on the original figure. That's why if we use the original figure, it will be extremely difficult to calculate the distance between M and N. However, if we like remove some of the faces and then the marked faces, and then somehow flatten them out so that they will level with the two faces on top, then it is very easy to compute the distance between points M and N by just applying the Pythagorean theorem. Alright, so the answer is option A, 10 units. Problem 26. Sylvia has several fair 12-sided dice, each with the numbers 1 to 12 written on their faces. If she rolls all the dice simultaneously, the probability of rolling exactly 1/12 is equal to the probability of not rolling a 12 at all. How many dice does Sylvia have? Suppose that there are n dice. Alright. The total number of outcomes must be 12 raised to n, since for each die there are 12 possible outcomes. So total outcomes in the sample space is 12 raised to n. Now, number of outcomes of getting exactly 1/12, outcomes for getting 1/12 must be equal to 11 raised to n minus 1 times n, because we only need one die to show up a 12 and the others numbers other than 12. Since we don't know on which die a 12 will come out, there are n possible ways where it can come out because there are n dice. So the total outcomes for getting 12 is 11 raised to n minus 1 times n. On the other hand, the outcomes of not getting a 12 is 11 raised to n, because we'll have to exclude the number 12 for each die. So outcomes for not getting a 12 is equal to 11 raised to n. Alright, now since the two probabilities indicated in the problem are equal, we must have the equation 11 raised to n over 12 raised to n equals 11 raised to n minus 1 times n over 12 raised to n. We can just cancel 12 raised to n. If we multiply both sides by 12 raised to n, then we can cancel that. And then we are left with 11 raised to n equals 11 raised to n minus 1 times n. Now let's divide both sides by 11 raised to n minus 1. We can cancel this, and so we have in the left side 11 raised to n minus 1 equals n. And so we have 11 in the left side because we cancel n, and then we are left with a positive 1. So 11 raised to 1, that's the same as 11. And so the answer is n equals 11. So there are 11 dice. That's option D. Problem 27. It is known that the statements 2 raised to x equals 3, 2 raised to y equals 7, and 6 raised to z equals 7 are true. Which of the following relationships is therefore correct? Alright. Notice that in the equation 6 raised to 7, 6 raised to z equals 7, we can actually break down 6 into 2 times 3. So this is 2 times 3 raised to z equals 7. Now notice that the 2 here, the 3 here, and the 7 in the right hand side can be replaced by 2 raised to x and 2 raised to y respectively. Alright, so the last equation becomes 2 times 2 raised to x raised to z equals 2 raised to y. Again, the 3 here is replaced by 2 raised to x, and then the 7 in the right hand side is replaced by 2 raised to y. Now, this is the same as 2 raised to x plus 1 raised to z equals 2 raised to y. Distribute the z inside, so that's 2 raised to z times x plus 1 equals 2 raised to y. Now take note the two numbers have the same base, which is 2. Therefore the exponents must be equal as well. So we have z times x plus 1 equals y. Divide both sides by x plus 1. Finally we get y over x plus 1, which is the same as letter A. So the answer is option A. Problem 28. A function f from R to R fulfills the condition f of 20 minus x is equal to f of 22 plus x for all real numbers x. It is known that f has exactly 2 real zeros. What is the sum of the 2 zeros? Alright. So suppose at x equals t, f of 20 minus t is equal to f of 22 plus t equals 0. This implies that 20 minus t and 22 plus t are zeros of f, right? And so the sum of the zeros is simply 20 minus t plus 22 plus t, which is equal to 42. Alright, so the answer is not among the options from A to D. So the answer here is option E. Problem 29. A special 4-digit number ABCD fulfills the equation ABCD equals A raised to A plus B raised to B plus C raised to C plus D raised to D. What is the value of A? We can first compute the following powers. 1 raised to 1 equals 1, 2 squared equals 4, 3 raised to 3 equals 27, 4 raised to 4 equals 256, 5 raised to 5 equals 3125, and if you notice 6 raised to 6 is equal to 46656. So really what we are going to test are these numbers, okay, from 1 raised to 1 up to 5 raised to 5, and see which one satisfies the condition. You can easily guess and check this one, you can check that the numbers 3 raised to 3 plus 3, 3 raised to 3 plus 4 raised to 4 plus 3 raised to 3 5 raised to plus 5 raised to 5 works. Okay, so that's 27 plus 256 plus 27 plus 3125. If you add these numbers, you'll get 3435. Alright, which satisfies the given equation. Now, we are only asked about the value of A. So the value of A is 3. So that's option B. Next, we have the last item. A game board is composed of 8 squares on which we want to stack coins. Initially, all squares are empty. On each turn, we choose 4 adjacent squares and place 1 coin on each of those squares. The numbers show how high the stacks are. Unfortunately, the table wobbled and 5 of the stacks fell over. How many coins were on the field indicated with a question mark before the stack fell? Alright, so let's examine small cases first. Let's create a sequence of 8 squares. And let's see what happens if we try to do the game in a few rounds. Okay, so let's create 8 squares, adjacent 8 squares. Alright, now instead of drawing coins, I'll just represent the coins by sticks. Okay, suppose in the first move we choose the first 4 squares, so we put 4 coins. So that's our first move. Now let's say in the second move we place coins here. Okay, third move, let's say here, and then fourth, let's say we have again the first 4 squares. Again, this is just arbitrary, just to see what happens in the sums, what pattern it gives. Let's say we have the last move. Let's have 4 coins here, or maybe we can add more. Let's have number 6 here. Alright, so this is our last move. Now let's total the coins for each square. First square 2, next is also 2, then we have 1 2 3 4, 1 2 3 4 5, next is 4, next is 4, next is 2, next is 1. Now notice that if we add the alternating coins, for example this one, this one, this one, and this one, so that's 2 plus 4 plus 4 plus 2, the result is 12. Now if we also add the other coins, this one, this one, this one, and this one, so we have 2 plus 5 plus 4 plus 1, the result is also 12. Alright, so what does this tell us? This tells us that the alternating sums are equal. So we will just apply the same process to the original problem. Now we assume that the stars here represent the same numbers, so we can say this is x, this one's x, x. Let's represent the question mark by y. This one is x. Now let's add this 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 one and this one to get what? We have 2x, right? 2x plus y plus 42. Okay, and then let's equate that to the other sum. This one 30, this one x, 36, and x. So what do we get? We get 2x plus 66. And now notice that we can cancel the 2x by transposing. And so y is equal to 66 minus 42, which is equal to 24. So the question mark on this square represents the number 24, and so the answer is option A.